Okay, hello everyone, and welcome back. We're going to again continue looking at modeling with quadratic functions and how we use quadratics in the real world. All right, today's objective, how to use quadratic functions to model real world situations. The essential question, and what kind of real world situations can be modeled using quadratics? Again, quadratic functions, you guys, they have a number of real world applications. It's one of the reasons we study them so hard in high school. Guys, obviously there's area, all right, and vertical and projectile or even orbital motion, all right, uses quadratics. Also, quadratics have a focal point like this. So they're used to make lenses and telescopes and microscopes and in your glasses and things like that, or satellite dishes. Look at how the satellite dishes shaped on the roof of your house, or a satellite we launch into outer space. Okay, it's shaped like a quadratic, and bridges sometimes have that look like that. All right, because they use it. It's a good structural advantage. If you look at the Martin Sabo Bridge across Hiawatha in Minneapolis, it looks like that. There's also electric field, a charged particle. When it enters an electric field, it starts to follow the path of a quadratic. Okay, as soon as it hits the electric field. Guys, for this lesson, we're going to look at three types of quadratic problems: the area with a frame, vertical motion problems, and a parabolic tunnel. And we've looked at all three of these last Friday. First, the area with a frame as an example. There's a company offers a rectangular pool with the size dimensions shown. So one side is twice as long as the other side. Okay? And has a 4-foot deck around the outside. Now, if we want a 15-foot wide pool, how many square feet will I need in my backyard available for the pool with the deck? All right, again, let X be the width of the pool. So the area is length times width. All right, so one side is 4 plus X plus 4. That's X plus 8. All right, the other side is 2X plus 4 plus 4. That's 2X plus 8. You can multiply those out, all right, and just put 15 in where X is, because we want a 15-foot wide pool. When I multiply those out, I see that I get 874 square feet. That's what I need available in my backyard to build a 15-foot wide pool with a deck. All right, guys, this is an area with a frame again, and this is a picture with a frame. Again, guys, if it's given, they're giving you, this is the function of the area right here. And they're asking, what are the length and width? Well, guys, this length times width gives this area. And remember, this is a quadratic. So a quadratic is two linear factors multiplied together. Length times width multiplied together. Length and width are distance. It's a linear distance. So you factor the quadratic. I got x plus 5 and x plus 2. And that is the length and width. I just leave it like that. X plus 5 and x plus 2. Guys, that particular problem, if we actually graphed that quadratic, we would have some answers down here where the area is negative. Obviously, guys, that doesn't make any sense. We can't have a negative area or a negative length to one of our sides. So sometimes, guys, when you do real-world problems, you get answers in math that don't make sense. All right, just keep that in mind. All right, the second type of problem we're going to look at is vertical motion. Guys, the vertical motion equation we'll be using is this one right here. We have a negative 16 in front. That's because we're going to be measuring all our vertical motion problems in feet per second. Okay, so that's why we have 16 in front. If we were measuring this in meters or something, it would be different. Okay, guys, t is the elapsed time. Sometimes we just use x for that. And don't let this h means height. Guys, but don't let that h be confused with the y component of the vertex. That's not what that is, okay? Again, we have the initial velocity and the initial height. It's what the b and the c are in our quadratic equation. As an example, a diver jumps off a platform here with initial vertical velocity of 16 feet per second. He just jumps off this platform. He's 30 feet above right here. Okay, 30 feet on the above on the top platform here. So here's our equation. All right, negative 16t squared plus 16t plus 30. Just put it right in there. Okay, that's the equation. Now, if they're asking how many feet above the platform will the driver be at his highest point, we have to find the y-coordinate of the vertex. All right, first we need to find k, or h, and then we need to find the y-coordinate of the vertex. Okay, so first we find the x-coordinate of the vertex using negative b over 2a. All right, so it takes a half a second to get to the top, half a second. Then plug in 1/2 into our original equation, and we find that he's 34 feet above the ground, above the pool at the highest point. So he's just 4 feet above the platform. You can think of it like that. And this is the vertex, 1/2 and 34. All right, guys, to find the maximum height above the water, if he dives from a 20-foot platform with an initial velocity of 8 feet per second. All right, so our equation is different. It becomes 8t plus 20. Okay, again, to find the top, how long it takes to get to the top, we use negative b over 2a. All right, and plug that in. I get 1/4. So just 1/4 of a second to get to the top. All right, you plug in 1/4 into this equation right here. We end up with 21 feet. All right, the driver's maximum height above the water is 21 feet. There's a real quick look at the graph of that one. And he starts up here at 20 and jumps up to 21 and then starts to come down into the pool. Guys, we can look at the intercept here to see how long until he enters the water. All right, it's 1.4 seconds. All right, for him to enter the water from the 20-foot platform. Now, when we factor this, we would get another answer over here. All right, negative 0.9, but that doesn't make sense. That's going backwards in time. Okay, remember, he takes off from right here and jumps up and then comes down. If you go backwards in time, yes, you would cross the x-axis again. That's where that negative number comes from, okay? Guys, the last one is the parabolic tunnel problem. And we looked at it on Friday. If the outline shape of the tunnel is a parabola or a quadratic, if the tunnel here is 100 feet wide, right, how tall is the tunnel at its highest point? Now, in this case, guys, just use the intercepts. Use the factored form. A is, again, negative 0.05. This one here is 0, so this x is just x minus 0. And this one over here is 100, so it's x minus 100. All right, the axis of symmetry obviously is going to be 50, right in the middle. That's our h. So you find k by plugging in 50 into this equation. I get 125. So the tunnel is 125 feet tall at its highest point. All right, y'all, that's it. Go ahead and complete the homework check. We will do it in class, too, on Tuesday. Guys, and these are the problems that are in the homework check, okay? All right, thanks. That's it.